Look up at the night sky tonight, and what you see is just the tiniest glimpse of reality, less than 5% of the universe as we know it, the rest. A vast, uncharted wilderness of cosmic mysteries waiting to be unraveled. Dark matter weaving invisible threads between galaxies, voids so enormous they defy logic, and forces like dark energy accelerating the very fabric of space itself. These aren't just abstract ideas, they're the hidden gears turning the machinery of existence, and we're only now beginning to decode their secrets. Think about that for a moment. Every star, every planet, every dazzling spiral of light we've ever observed is just a fraction of what's really out there. The Hubble Deep Field taught us this in a single, humbling image. A speck of sky, seemingly empty, revealed thousands of galaxies when we peered deeper. What else lies beyond our vision? The answer could rewrite the laws of physics, redefine our place in the cosmos, and maybe even reveal truths about reality we're not yet ready to comprehend. That's the thrill of the Uncharted. It's not just about mapping the unknown, but about discovering how much we've yet to imagine. This journey isn't for the faint of heart. We'll venture into territories where time bends, where matter vanishes, and where the universe itself might be a projection of something far stranger. From rogue planets drifting through eternal night to the eerie signals of fast radio bursts pulsing from the void, each discovery peels back another layer of the cosmic onion. And here's the best part: you don't need a telescope to join the adventure. All you need is curiosity. So buckle up, we're about to dive into the deepest questions science can ask, and the answers might just leave you speechless. The cosmos is calling. Let's see what it has to say. When we talk about the uncharted regions of the universe, it's easy to picture distant galaxies or unexplored corners of space, but the truth is far stranger. Some of the most profound mysteries aren't places at all, but colossal gaps in our understanding. Take dark energy, for instance. It's not a distant nebula or a hidden planet. It's a fundamental force accelerating the expansion of the cosmos, and we have no idea what it actually is. Then there's quantum space-time, a realm where the very fabric of reality churns with unpredictability at scales so tiny they defy observation. These aren't just unanswered questions, they're entire frontiers where our current laws of physics start to unravel. Consider the Hubble Deep Field, one of the most humbling images ever captured. Astronomers pointed the Hubble Space Telescope at what seemed like an empty patch of sky, no larger than a grain of sand held at arm's length. What they found was staggering: thousands of galaxies, each containing billions of stars, all crammed into that tiny, seemingly void space. If that's what exists in a single speck of nothingness, how much more lies beyond our gaze? The sheer scale of the universe is almost incomprehensible, and that's before we even account for the fact that we're limited by the speed of light. We can only see so far because light from the most distant regions hasn't had time to reach us yet. It's like standing in a foggy forest, only able to see the trees closest to you, while knowing an entire unseen wilderness stretches beyond. But the challenge isn't just about distance or scale. Some of these cosmic puzzles are invisible by their very nature. Dark matter, for example, doesn't emit, absorb, or reflect light, yet its gravitational pull is the glue holding galaxies together. We know it's there because without it, the universe as we understand it wouldn't make sense. But detecting something that doesn't interact with light is like trying to map a city using only sound. You might hear echoes, but the full picture stays frustratingly out of reach. This is why scientists have to rely on indirect methods, studying the way gravity bends light around galaxy clusters or tracking the strange motions of stars within galaxies. Every breakthrough peels back another layer of the mystery, revealing just how much we still don't know. What makes these uncharted regions so thrilling isn't just their mystery, it's the way they force us to rethink everything. Every time we push the boundaries of observation or invent new tools to probe deeper, the universe seems to respond with even bigger questions. And that's the beauty of exploration, whether it's across oceans or across the cosmos. The unknown isn't just a destination, it's the engine that drives discovery forward. Imagine holding a massive, spinning top in your hands. The faster it spins, the more force tries to fling its pieces outward, yet somehow it stays perfectly intact. Now picture our Milky Way galaxy as that spinning top, with stars whirling around its center at mind-bending speeds. Here's the puzzle: there isn't enough visible matter, stars, gas, dust, to generate the gravity needed to hold everything together. The math just doesn't add up. That's where dark matter steps in, or rather, where we've had to imagine it. This invisible scaffolding makes up 27% of the universe, weaving an unseen web that holds galaxies in place like cosmic glue. Without it, stars at the edges of galaxies would simply drift off into the void, unmoored by gravity's weakening grip. But how do you study something you can't see, touch, or even detect directly? Scientists have turned to brilliant workarounds. One approach involves watching how light bends around massive galaxy clusters, a phenomenon called gravitational lensing. The amount of bending reveals how much mass, visible or not, is distorting spacetime. Another clue comes from the cosmic microwave background, the faint afterglow of the Big Bang, where subtle temperature fluctuations hint at dark matter's fingerprints on the early universe. Then there are experiments like the Large Hadron Collider, smashing particles together at nearly the speed of light, hoping to create a dark matter particle in the debris. Telescopes like Euclid, set to map the sky in unprecedented detail, are hunting for distortions in the shapes of billions of galaxies, tracing dark matter's hidden influence. So what could dark matter actually be? Leading candidates include weakly interacting massive particles, or WIMP hypothetical particles that barely interact with normal matter except through gravity. Then there are actions, ultra-light particles theorized to solve a different physics puzzle but could also explain dark matter's ghostly presence. Some even speculate about primordial black holes formed in the universe's chaotic first moments. But here's the catch: despite decades of searching, no experiment has definitively caught dark matter in the act. It's like trying to identify a shadow by the shape it casts. You know it's there, but the substance remains elusive. The stakes couldn't be higher. Dark matter isn't just a cosmic placeholder. It's the architect of the large-scale structure of the universe. Simulations show that without it, galaxies wouldn't have formed in the way we observe. Its gravitational pull sculpted the cosmic web, the vast filaments of galaxies stretching across the emptiness of space. And yet, for all its importance, dark matter remains one of science's most tantalizing enigmas. Every null result, every failed detection, only deepens the mystery because the universe keeps insisting it's there, even as it hides in plain sight. This brings us to the next frontier: dark energy, the even more mysterious force accelerating the expansion of the cosmos. But that's a story for another moment. For now, dark matter stands as a testament to the universe's ability to keep its deepest secrets just out of reach, challenging us to look beyond what we can see and rethink the very nature of reality itself. Picture a balloon inflating, but instead of slowing down as it grows larger, it starts expanding faster and faster, defying all expectations. That's precisely what astronomers witnessed in the late 1990s when they studied distant supernova, expecting to measure how much the universe's expansion was slowing due to gravity. Instead, they found the opposite. The cosmos wasn't just growing, it was accelerating. This baffling discovery pointed to something even more mysterious than dark matter, dark energy, an invisible force making up a staggering 68% of the universe's total content. Unlike gravity, which pulls things together, dark energy behaves like an anti-gravity, pushing space itself apart. But what exactly is this enigmatic force? One leading idea is the cosmological constant, a concept Einstein once proposed and later dismissed as a property of empty space itself. Imagine space as a vast, bubbling sea where even a complete vacuum crackles with energy. This inherent energy could be driving the acceleration, a static, unchanging feature woven into the fabric of reality. Yet there's a problem. Theoretical predictions for how strong this energy should be are off by a factor of 1 followed by 120 zeros. That's not just a rounding error, it's the largest mismatch in science. Alternative theories suggest dark energy might not be constant at all, but a dynamic field slowly evolving over time. Some call it quintessence, a fluid-like substance with repulsive gravity that could wax or wane. If true, this would mean the universe's fate isn't set in stone. To test these ideas, projects like the Dark Energy Survey map millions of galaxies, tracking how their clustering changes across cosmic history. Supernovas serve as cosmic mile markers, their brightness revealing how fast space stretched during their explosions' light journeys to Earth. The implications are staggering. If dark energy strengthens, it could lead to a big rip, tearing galaxies, stars, and even atoms apart. If it weakens, gravity might regain dominance, collapsing the universe in a big crunch. Or it might balance perfectly, allowing expansion to continue gently forever. Right now, we're like sailors trying to predict a storm's path while barely understanding the wind. Each observation peels back another layer of the mystery, revealing just how much we still don't know about the forces shaping reality itself. This isn't just academic curiosity. Dark energy's behavior holds the key to the universe's ultimate destiny. And as we grapple with its secrets, we're forced to confront an even deeper question. Are we seeing the true nature of reality, or just the shadow of something far stranger? The answers might lie in the most desolate regions of space, where dark energy's influence reigns unchallenged, the cosmic voids. If you think space is already overwhelmingly vast, wait until you hear about cosmic voids, regions so empty they make the deepest reaches of intergalactic space seem crowded. Picture a bubble hundreds of millions of light years across, containing almost no galaxies, stars, or even detectable matter. The Boötes void, one of the largest known, could fit 60 Milky Ways side by side with room to spare, yet it holds fewer than 60 galaxies total. That's like finding a single grain of sand in an Olympic-sized swimming pool. These aren't just gaps in the cosmic map, they're fundamental mysteries that rewrite our understanding of how the universe structures itself. What makes these voids so baffling is how they defy expectations. According to standard models of galaxy formation, matter should be distributed relatively evenly, with slight variations from quantum fluctuations in the early universe. But voids like Boötes are far emptier than those models predict. One theory suggests dark energy played a role. Its repulsive force might have pushed matter outward from these regions, creating vast deserts in spacetime. Others propose that voids are relics of the universe's infancy, when primordial sound waves called baryon acoustic oscillations left behind underdense regions as they rippled through the hot, dense plasma of the Big Bang's aftermath. Yet voids aren't just empty space, they're active players in the cosmic web. Galaxies aren't randomly scattered. They cluster along filaments that wrap around voids like threads around a balloon. These filaments, made of dark matter and gas, act as highways for galaxy formation, funneling matter into dense knots where galaxies collide and merge. Meanwhile, the voids themselves exert a sort of negative gravity, repelling nearby matter and shaping the large-scale flow of the universe. Astronomers call this the void effect, and it might explain why some galaxy clusters move in unexpected directions, as if tugged by invisible hands. The study of voids isn't just academic, it's a window into dark energy's influence. If voids grow faster than simulations predict, it could mean dark energy is stronger than we thought, accelerating the universe's expansion in ways we don't yet understand. Telescopes like the Dark Energy Spectroscopic Instrument are mapping millions of galaxies to measure how voids evolve over time, offering clues to one of cosmology's biggest puzzles. But here's the strangest part: voids might not be completely empty. Some theories suggest they could harbor rogue planets, orphan stars, or even exotic particles that don't interact with light. These lonely wanderers, if they exist, would drift through perpetual darkness, untouched by the gravitational dance of galaxies. It's a haunting thought that the emptiest places in the universe might still hide secrets waiting to be discovered. This brings us to the next frontier, the nomads of the cosmic dark, rogue planets untethered to any star. But that's a story for another moment. For now, voids stand as a reminder of how much we still don't understand about the universe's grand architecture, and how even emptiness can shape the fate of everything. Picture a planet not orbiting a star, not basking in the warmth of a sun, but drifting alone through the frigid darkness between stars. These are rogue planets, cosmic nomads untethered from any solar system, and they're far more common than we once thought. Billions, perhaps even trillions of these solitary worlds likely wander the Milky Way, invisible to traditional telescopes because they emit almost no light. Yet some, like PSOJ 3-18.522, betray their presence with a faint infrared glow, the last whispers of heat left over from their violent births or turbulent pasts. How do planets end up adrift in the void? There are two leading theories, each more dramatic than the last. The first suggests they were violently ejected from their home solar systems during the chaotic gravitational dance of planet formation. Imagine a young star system where giant planets like Jupiter jostle for position, their gravitational pulls flinging smaller siblings into the abyss. The second possibility is even stranger. Some rogue planets may have formed in isolation, collapsing directly from clouds of gas and dust too small to ignite into stars. These failed stars, known as sub-brown dwarfs, blur the line between planet and star, challenging our definitions of what a world even is. Detecting these dark wanderers requires ingenious methods. Microlensing, for example, exploits the way a rogue planet's gravity bends and magnifies the light of a distant star as it passes in front, a fleeting signal that hints at the unseen. Infrared telescopes like NASA's upcoming Nancy Grace Roman Space Telescope will scan the skies for their faint thermal signatures. Already, surveys have uncovered rogue planets with masses ranging from gas giants to Earth-sized bodies, suggesting a staggering diversity in these lone travelers. But here's the most tantalizing question: could they harbor life? Without a star's warmth, surface conditions would be brutally cold, but beneath icy crusts, geothermal heat or radioactive decay might sustain subsurface oceans just like those suspected on moons like Europa or Enceladus. Some scientists speculate that rogue planets could be dark arcs, carrying microbial life across interstellar space, seeding the galaxy with biology wherever they drift. For future interstellar travelers, these worlds might even serve as waypoints, silent, frozen oases in the vast desert between stars. Their existence reshapes our understanding of planetary formation. If rogue planets outnumber stars, as some studies suggest, then the universe is far more dynamic and chaotic than we imagined. Solar systems might not be the orderly, stable neighborhoods we once pictured, but tempestuous nurseries where planets are born, ejected, and scattered like cosmic dice. And if life can persist in the perpetual night of a rogue world, then the potential for biology in the universe expands beyond the traditional, habitable zone of stars into the cold, dark frontier between them. This raises another mystery. What happens to the stars left behind when planets are torn away? Some, we now know, become orphan stars, cast adrift in the spaces between galaxies, their stories just as compelling as the rogue planets they once hosted. But that's a tale for another moment. For now, the rogue planets remind us that the universe is wilder, stranger, and more untamed than we ever dreamed, with secrets lurking even in the darkest, loneliest corners of the void. Imagine a star not as part of a glittering galaxy, but as a lone traveler in the black expanse between them, untethered, unseen, and utterly alone. These are orphan stars, celestial castaways flung into the abyss by the violent forces of galactic collisions or the gravitational tug of war between massive galaxies. Unlike rogue planets which drift within galaxies, orphan stars exist in the most desolate reaches of intergalactic space, where the nearest neighbor might be millions of light years away. The Hubble Space Telescope first uncovered their ghostly presence in the Virgo cluster, detecting a faint, diffuse glow. The combined light of billions of these solitary stars, a cosmic echo of their turbulent past. How do stars end up so far from home? The answer lies in the chaos of galactic mergers. When galaxies collide, their gravitational interactions can slingshot stars into the void like stones from a catapult. Others are stripped away by tidal forces, like grains of sand pulled from a beach by a retreating wave. These events leave behind trails of stars, faint and scattered, often too dim to spot individually. Yet collectively, their light creates an eerie backdrop, a phenomenon astronomers call intracluster light. Studying this glow offers clues about the violent histories of galaxy clusters, revealing ancient collisions we'd otherwise never detect. But here's the most intriguing question: could these orphan stars have planets? If so, their worlds would exist in perpetual twilight, bathed only in the meager light of their solitary suns. Without the radiation and gravitational disturbances of a crowded galaxy, these systems could be eerily stable, perfect laboratories for studying how stars age in isolation. Any planets orbiting them would face extreme conditions: no day-night cycle, no neighboring stars, and temperatures hovering near absolute zero. Yet life, if it existed, might find a way in subsurface oceans warmed by tidal forces or geothermal activity. The possibility, however remote, forces us to rethink the boundaries of habitability in the universe. Orphan stars also challenge our understanding of stellar evolution. In galaxies, stars interact with gas clouds, neighboring stars, and magnetic fields, all shaping their life cycles. But in the void, a star evolves in near-total isolation, free from external influences. This makes them cosmic time capsules, preserving information about their origins in ways galactic stars cannot. For astronomers, they're like control experiments, a way to study stars without the noise of their bustling galactic environments. Yet these lonely giants aren't the only solitary phenomena lurking in the darkness. The voids between galaxies might hide even stranger objects: black holes ejected during galactic mergers, rogue neutron stars, or the elusive dark matter particles that refuse to reveal themselves. The discovery of orphan stars opens a door to a broader mystery. What else exists in the vast, uncharted tracts of intergalactic space? The answer might lie in the brief, brilliant signals we've only begun to decipher. fast radio bursts, fleeting pulses of energy that could be the next clue in our quest to map the universe's hidden frontiers. One moment, the universe is silent. The next, a blast of radio waves brighter than 1 billion suns rips through the cosmos, lasting just a few thousandths of a second before vanishing without a trace. These are fast radio bursts, or FRB, and they're among the most baffling signals we've ever detected. First discovered in 2007, these pulses travel billions of light years to reach us, carrying energy equivalent to what our sun emits in decades. Some burst once and disappear forever. Others, like FRB 1211, repeat in unpredictable patterns, flickering like a cosmic strobe light. The sources unknown, the causes pure speculation. What makes FRBs so tantalizing is their sheer unpredictability. Imagine trying to study a lightning bolt that appears at random, anywhere on Earth with no warning. That's the challenge astronomers face. Telescopes like CHIME, the Canadian Hydrogen Intensity Mapping Experiment, scan vast swaths of sky daily, catching these fleeting signals in real time. Each new detection adds a piece to the puzzle, but the picture only grows stranger. Some FRBs are highly polarized, suggesting they pass through intense magnetic fields near neutron stars or black holes. Others show bizarre frequency structures, as if the signal was scrambled by some unseen cosmic lens. So what could possibly generate such extreme bursts? Leading theories range from cataclysmic collisions like two neutron stars merging, to eruptions from magnetars, ultra-dense stellar corpses with magnetic fields 1 trillion times stronger than Earth's. Then there's the more speculative idea: could they be artificial? Some have proposed alien megastructures like interstellar beacons or even power beams for light sails. While unlikely, the possibility forces us to confront how little we truly understand about these signals. But FRBs aren't just cosmic oddities, they're also tools. As these radio waves traverse the universe, they interact with the sparse matter between galaxies, slowing slightly in a process called dispersion. By measuring this delay, astronomers can map the otherwise invisible, missing baryonic matter, the ordinary protons and neutrons that should exist but evade detection. It's like using a flashlight in fog. The way the beam scatters reveals the density of the mist. Already, FRBs have helped locate huge reservoirs of this elusive matter, solving part of a decades-old cosmic accounting problem. Yet with every answer comes a new question. Why do some FRBs repeat while others don't? What creates their intricate frequency patterns? And why do a few seem to originate from relatively nearby galaxies, while most come from the universe's deepest reaches? Each discovery peels back another layer of the mystery, reminding us that the cosmos is far stranger than we've dared to imagine. And as we chase these ghostly signals, we're led to an even more profound enigma: the monstrous gravitational engines that might lurk behind them, supermassive black holes. At the heart of nearly every galaxy, including our own Milky Way, lurks a monster, a gravitational behemoth so dense that not even light can escape its grasp. These supermassive black holes, like Sagittarius, a star at our galaxy's core, weigh millions to billions of times more than our sun, crammed into a space smaller than our solar system. Their existence was once theoretical. Now we've not only confirmed them but captured their shadow in the Event Horizon Telescope's historic first image of M87's black hole. Yet for every answer, these cosmic giants pose 10 new questions, starting with the most perplexing of all. How did they grow so unimaginably large in what seems like no time at all? The timeline simply doesn't add up. Some supermassive black holes existed when the universe was less than 700 million years old, cosmic infants by universal standards. For them to reach billions of solar masses so quickly, they'd need to consume matter at impossible rates, violating known physics. This paradox has led to radical theories. Perhaps they weren't born from collapsing stars like smaller black holes, but formed directly from collapsing clouds of primordial gas in the early universe's dense environment. Or maybe dark matter, the invisible scaffolding of the cosmos, played a role, with certain hypothetical particles called dark matter black holes providing seeds that grew rapidly. There's even speculation about quasi-stars, hypothetical early universe objects with black holes at their cores that fed on the surrounding star's plasma like cosmic parasites. But their formation is only half the mystery. Supermassive black holes actively shape their galaxies in ways we're only beginning to understand. When matter spirals into them, forming glowing accretion disks heated to millions of degrees, some gets funneled into powerful jets shooting out at nearly light speed. These jets can stretch for millions of light years, influencing star formation across entire galaxies. Too much activity, and they sterilize their host galaxies by blowing away star-forming gas. Too little, and stars might not form efficiently at all. It's a delicate balance, making these black holes cosmic regulators as much as destroyers. Then there's the event horizon, the point of no return where gravity's grip becomes absolute. Beyond this boundary, space and time switch roles, and our understanding of physics breaks down completely. The Event Horizon Telescope's images give us our first glimpses of this threshold, showing light bent into a fiery ring around the black hole's shadow. But what happens inside? Some theories suggest the singularity. The black hole's infinitely dense core might be a gateway to other universes or dimensions. Others propose it's a firewall of quantum chaos, where information gets scrambled beyond recognition. The truth could force us to rewrite Einstein's theory of general relativity, or finally unite it with quantum mechanics. What makes supermassive black holes truly humbling is realizing they're not cosmic anomalies, they're fundamental to how the universe works. Every massive galaxy seems to have one, suggesting their formation and evolution are deeply entwined with the galaxies themselves. They're the ultimate paradoxes, simultaneously the simplest objects in the universe defined only by mass, spin, and charge, and the most complex, warping spacetime in ways that still defy our comprehension. As we push our telescopes to new limits, from gravitational wave detectors to next-generation space observatories, each discovery peels back another layer of their mystery, revealing not just how black holes work, but how the fabric of reality itself might be far stranger than we ever imagined. This dance between the incomprehensibly large and the infinitesimally small leads us to the next frontier, quantum foam, where the very structure of spacetime might dissolve into a seething, probabilistic chaos at the smallest scales. But that's a journey into a realm where even our best physics becomes more poetry than prediction. At the smallest scales, imaginable trillions of times tinier than an atom, the smooth fabric of spacetime might not be so smooth after all. Instead, it could be a turbulent, frothing sea of fleeting particles and microscopic wormholes, popping in and out of existence in a frenzy of quantum activity. This is the bizarre world of quantum foam, a concept so radical it challenges our most fundamental ideas about reality. Picture the surface of a calm lake on a windless day, seemingly flawless and still. But zoom in closer, and you'd see molecules jostling violently, colliding and creating tiny whirlpools. Now imagine that same chaotic dance, but applied to the very fabric of the universe itself. That's quantum foam, spacetime not as a stage, but as an ever-shifting, seething participant in the cosmic drama. The idea emerged from combining two pillars of modern physics, quantum mechanics and general relativity, and realizing they paint conflicting pictures of spacetime. Quantum mechanics says uncertainty rules the subatomic world. Particles flicker in and out of existence, borrowing energy from nowhere as long as they repay it quickly. General relativity describes spacetime as a smooth, bendable sheet warped by mass. But at the Planck scale, a distance so small it makes atoms look like planets, these theories clash. Quantum foam is the proposed compromise, a realm where spacetime itself becomes fuzzy and unpredictable, riddled with microscopic black holes and tunnels that appear and vanish in an instant. Could this chaos hold the key to some of the universe's biggest mysteries? Some theorists suggest quantum foam might explain dark energy, the mysterious force accelerating cosmic expansion. If spacetime is frothing with energy at the smallest scales, that bubbling activity could manifest as a repulsive force on cosmic scales. Others speculate that these fleeting wormholes, if stabilized by exotic matter with negative energy, might one day enable warp drives, not by moving through space, but by bending spacetime itself into shortcuts between distant points. It's the kind of idea that straddles the line between hard science and science fiction, yet emerges directly from the math. The challenge, of course, is proving any of this. We can't peer directly at the Planck scale. It's like trying to spot a marble on the moon with a telescope made of fog. But ingenious experiments are hunting for indirect clues. Gravitational wave detectors like LIGO could potentially detect subtle distortions caused by quantum foam's turbulence, if the effect is strong enough. Other proposals involve ultra-precise atomic clocks, measuring whether time itself stutters at microscopic scales, a telltale sign of spacetime's grainy nature. Each test pushes technology to its limits, probing a frontier where the very concepts of here and now start to break down. What makes quantum foam so thrilling isn't just its strangeness. It's the possibility that this subatomic chaos could bridge the last great divide in physics. For decades, physicists have struggled to unite quantum mechanics and general relativity into a single theory of everything. Quantum foam, or some version of it, might be the missing link, showing how gravity emerges from the quantum realm's probabilistic dance. Or it might reveal something even weirder, that spacetime isn't fundamental at all, but emerges from deeper, more abstract building blocks we've yet to imagine. As we pull back from this microscopic frenzy, we're reminded that the universe's structure, from the quantum foam underfoot to the vast cosmic web overhead, is more interconnected than we ever realized. Each scale whispers clues about the others, hinting at a grand unity hidden in plain sight. And that brings us to the next chapter of our journey, the immense, galaxy-strewn architecture of the cosmos itself, where dark matter's invisible hand sculpts the universe into a web of breathtaking scale and complexity. If you could step back and view the universe from afar, you wouldn't see scattered galaxies drifting randomly through the void. Instead, you'd witness an intricate, sprawling tapestry, a cosmic web stretching across billions of light years, with galaxies clustered like glittering beads on invisible strings. This vast structure isn't random. It's the universe's skeleton, woven from the gravitational pull of dark matter. The web's filaments, some hundreds of millions of light years long, serve as highways for galaxy formation, funneling gas and stars into dense knots where massive clusters collide and merge. These intersections, known as nodes, are the universe's metropolises, home to thousands of galaxies bound together by gravity's unrelenting grip. How do we know this web exists if dark matter is invisible? The answer lies in the way galaxies move. Just as leaves floating on a river's surface reveal the water's hidden currents, galaxies trace the contours of dark matter's gravitational field. Supercomputers like Illustris TNG simulate this process, starting with the faint ripples left by the Big Bang and watching as gravity sculpts them into the web we observe today. These simulations match reality with uncanny precision, predicting where galaxies should cluster and how filaments thread through the voids. Yet there's a catch: mapping the real cosmic web is painstakingly slow. Unlike simulations, which can fast forward through billions of years, astronomers must piece together the universe's structure one painstaking observation at a time, using redshift surveys and gravitational lensing to infer the dark matter's hidden architecture. The cosmic web isn't just a static relic, it's a dynamic, evolving entity. Filaments act as conduits, channeling gas into galaxies and feeding their supermassive black holes. Collisions between galaxy clusters, like the Bullet Cluster, strip away normal matter while dark matter plows ahead, leaving ghostly imprints of its presence. These crashes are cosmic gold mines, revealing how dark matter interacts or doesn't with itself and the rest of the universe. Meanwhile, the web's emptiest regions, the voids, exert their own influence, repelling matter and shaping the large-scale flow of galaxies in ways we're only beginning to understand. But the web's grandest mystery isn't its structure, it's why it looks the way it does. The distribution of galaxies aligns eerily with predictions based on dark matter's gravitational pull, yet small discrepancies linger. Some filaments appear thicker or more sparse than simulations suggest. Others twist in unexpected directions, as if tugged by forces we haven't accounted for. Could these anomalies hint at unknown properties of dark matter, or do they point to something even stranger, like the influence of dark energy on the web's growth? Every new map deepens the intrigue, revealing a universe more complex and interconnected than we ever imagined. This brings us to the web's most enigmatic hubs, the galaxy clusters anchoring its nodes. These colossal assemblies, like the Coma Cluster or El Gordo, are laboratories for extreme physics, where gas heats to millions of degrees and black holes merge in spectacular explosions. They are also time capsules, preserving clues about how the cosmic web formed in the universe's infancy. By studying their shapes, temperatures, and motions, astronomers can trace the web's evolution and perhaps uncover why it took this particular form instead of another. The cosmic web is more than just a backdrop for galaxies. It's the stage upon which the universe's story unfolds. Its filaments dictate where stars will ignite, where black holes will feast, and where future civilizations might one day rise. And as we peel back its layers, we're left with a humbling realization. The universe isn't just expanding, it's organizing itself on scales so vast, they defy comprehension. But even this intricate web holds anomalies like the cold spots in the cosmic microwave background that challenge our understanding of its origins. And that's where the next mystery begins. In the afterglow of the Big Bang, a faint whisper of radiation lingers, the cosmic microwave background, or CMB. This ancient light, dating back to when the universe was just 380,000 years old, serves as a baby picture of the cosmos, revealing the seeds of all future structure. But there's a peculiar blemish in this otherwise smooth snapshot: the CMB cold spot, a region spanning nearly 1 billion light-years where the temperature dips unexpectedly. It's not just slightly cooler, it's a dramatic anomaly standing out like a frozen thumbprint on the universe's warm canvas. So what could explain this cosmic chill? One possibility is a statistical fluke, a random quantum fluctuation amplified over billions of years. But the odds of such an extreme deviation occurring by chance are less than 1 in 100, making it as unlikely as rolling the same number on a die 50 times in a row. That's led scientists to consider more exotic explanations. One tantalizing idea is the imprint of a parallel universe, a bubble of space-time brushing against our own in a hypothetical multiverse. While speculative, this theory suggests the cold spot might be a bruise left by a cosmic collision between universes, a remnant of physics beyond our own. Then there's the supervoid hypothesis. If the cold spot corresponds to an enormous, underdense region of space, a void within a void, its emptiness could subtly cool light passing through it via a phenomenon called the integrated Sachs-Wolfe effect. Think of it like climbing out of a valley. Photons lose energy as they escape the void's weakened gravity, shifting the CMB's temperature. The problem: a void large enough to explain the cold spot would dwarf any known structure, stretching the limits of our understanding of cosmic evolution. Surveys have hunted for such a supervoid, but none match the required scale, leaving this idea in limbo. The Planck satellite's meticulous measurements only deepened the mystery. Its data confirmed the cold spot's existence, but couldn't definitively link it to any known structure or anomaly. Some researchers argue the cold spot might be a confluence of smaller voids, while others propose it's evidence of cosmic textures, defects in spacetime left over from the universe's violent infancy. What's clear is that the cold spot challenges our assumptions about the universe's uniformity. The CMB is supposed to be the ultimate test of cosmological models, a near-perfect blackbody with tiny, predictable fluctuations. Yet here, in this one patch, the rules seem to bend. This enigma ties into a broader puzzle, the missing baryons. The cold spot's peculiarities hint at gaps in our inventory of ordinary matter protons and neutrons that should exist but evade detection. If the void explanation holds, its lack of visible matter might align with the universe's missing baryon problem, suggesting vast reservoirs of hidden material lurking in the cosmic web's darkest recesses. As we grapple with the cold spot's secrets, we're reminded that even our most precise cosmic maps contain uncharted territories, regions where the universe refuses to conform to expectations. Whether it's a window into parallel realities, a ghostly void, or something entirely unforeseen, this anomaly underscores how much we have yet to learn about the fabric of reality itself. And as we turn our gaze to the missing baryons, we confront another piece of the cosmic puzzle. Where exactly has half the universe's ordinary matter gone? We've mapped galaxies, black holes, and even the cosmic web, but there's a glaring hole in our cosmic inventory. Literally, half the universe's ordinary matter, the protons and neutrons that make up everything from stars to smartphones, is missing. This isn't dark matter or some exotic substance. It's the very stuff we're made of, and somehow, it's slipped through our observational nets. The Big Bang's equations tell us exactly how much baryonic matter should exist, yet when we tally up all the stars, gas, and dust we can see, we're left with a cosmic IOU for nearly 50% of the universe's expected normal mass. So where is it hiding? One leading suspect is the warm-hot intergalactic medium, or WIM, a vast, diffuse web of gas so hot it's invisible to optical telescopes, but just cool enough to evade most X-ray detectors. Picture steam rising from a boiling pot. You might not see it until sunlight hits it just right. Similarly, the WIM faint filaments threading between galaxies only betray their presence when backlit by distant quasars or when their oxygen atoms absorb specific wavelengths of light. Recent studies using the Hubble Space Telescope have caught glimpses of this shadowy reservoir, spotting the fingerprints of highly ionized oxygen in the light from faraway quasars, like finding a hidden message written in the steam of that boiling pot. Then there's the cosmic web's denser filaments, where theorists predict much of the missing matter could be pooled in sprawling rivers of warm gas. These aren't the bright, glowing strands we see in simulations, but faint, nearly transparent channels that might only reveal themselves through subtle distortions in the cosmic microwave background, or the way they bend X-rays from distant galaxy clusters. Missions like ESA's Athena X-ray Observatory, set to launch in the 2030s, are designed to hunt these elusive structures, scanning the sky for the faint X-ray glow of million-degree gas. If successful, they could finally close the gap in our cosmic ledger, confirming that the missing baryons have been hiding in plain sight all along. But why does this matter? Beyond balancing the universe's books, finding these baryons would validate our most fundamental models of cosmic evolution. The Big Bang's predictions about the abundance of light elements like hydrogen and helium hinge on knowing how much ordinary matter exists. If half of it has truly vanished, it could mean our understanding of nucleosynthesis, how atoms formed in the universe's first minutes, is flawed. Alternatively, the missing matter might hint at unknown processes that ejected baryons from galaxies or even transformed them into something else entirely. The search for these lost particles is more than a cosmic scavenger hunt. It's a test of whether we truly understand the universe's scaffolding. And as we piece together the clues, we're reminded that even the most familiar ingredients of reality can defy our expectations. Now, with the mystery of the missing baryons still unresolved, we turn our gaze to the edge of the observable universe, to a galaxy so distant, its light is a messenger from the cosmic dawn itself, GNZ 11. GNZ 11 isn't just a galaxy, it's a time capsule, a shimmering beacon from an era when the universe was a mere 400 million years old. To put that in perspective, this galaxy's light began its journey to us when Earth was nothing more than a swirl of cosmic dust, over 8 billion years before our planet even formed. What makes GNZ 11 so extraordinary isn't just its age, but how it upends our understanding of the cosmic dawn, that twilight period when the first stars and galaxies flickered to life. Most theories predicted that early galaxies would be small, faint, and chaotic building blocks of the universe still learning how to assemble themselves. But GNZ 11 defies those expectations. It's massive, luminous, and teeming with stars forming at a rate 20 times faster than the Milky Way does today. It's like finding a skyscraper in the middle of a prehistoric wilderness, something that, by all accounts, shouldn't be there. How did such a mature galaxy emerge so quickly after the Big Bang? One possibility is that star formation in the early universe was far more efficient than we thought. Without heavy elements to cool gas clouds and slow their collapse, the first stars might have formed in violent bursts, seeding galaxies with stellar populations almost overnight. Another theory suggests that dark matter played a bigger role than we realized, clumping together faster than models predict and pulling ordinary matter into dense, star-forming pockets sooner than expected. Or perhaps GNZ 11 isn't alone. What if it's part of a hidden population of early giants, lurking just beyond the edge of our current observations? This is where the James Webb Space Telescope enters the story. With its infrared eyes, JWST can peer even further back in time, searching for galaxies that formed just 200 million years after the Big Bang, a mere blink in cosmic terms. Early observations have already revealed candidate galaxies that, if confirmed, could push the record for the oldest known galaxy even closer to the universe's birth. Each new discovery raises the same tantalizing question: how far back does the chain go? Was there a first galaxy, or did star formation ignite across the cosmos in a near-simultaneous flash, like fireflies lighting up in a dark forest? But GNZ 11's greatest mystery isn't just how it formed, it's what came before it. The galaxy's existence hints at an even earlier epoch, a time when the universe was too hot and dense for stars or galaxies to exist at all. This was the era of cosmic inflation, a fraction of a second after the Big Bang, when space-time itself expanded faster than light, stretching quantum fluctuations into the seeds of all future structure. Those primordial ripples frozen into the fabric of the universe would eventually grow into the galaxies, clusters, and filaments we see today. GNZ 11, in all its brilliance, might just be one of the first flowers to bloom from those ancient seeds. The deeper we look, the more the universe surprises us. GNZ 11 isn't an endpoint, it's a doorway, inviting us to step further back into the shadows of cosmic history, toward the moment when time itself began. And as we cross that threshold, we're forced to confront the next great mystery. What unleashed the universe's explosive birth in the first place? The answer lies in the inflationary epoch, a phenomenon so powerful it shaped everything that followed, yet remains one of the most elusive chapters in the story of our cosmos. In the very first moments of existence, the universe didn't just expand, it exploded outward with unimaginable speed, stretching from smaller than an atom to the size of a grapefruit in less than a trillionth of a second. This mind-bending event, known as cosmic inflation, wasn't like the steady expansion we see today. It was a runaway growth spurt, inflating space-time faster than light itself could travel. And while that might sound like science fiction, it's the leading explanation for one of the cosmos' most puzzling features, the eerie uniformity of the cosmic microwave background. No matter where we look, the CMB's temperature is almost identical down to a few hundred thousandths of a degree. Without inflation, regions of the universe now billions of light-years apart could never have reached thermal equilibrium. It's as if every corner of a vast auditorium spontaneously erupted into perfect harmony, despite never having exchanged a single note. But what could have sparked such an extreme event? One possibility lies in the quantum realm. Imagine the newborn universe as a seething foam of virtual particles, where tiny fluctuations in energy could have triggered a phase transition. Like water suddenly freezing into ice, releasing a burst of repulsive gravity that sent space-time racing outward. Another theory ventures into higher dimensions, suggesting our universe might be a four-dimensional brain colliding with another in a higher dimensional space, the shock wave igniting inflation. These ideas straddle the line between physics and metaphysics, pushing the boundaries of what we can test. That's where experiments like BICEP and Keck come in. Perched in the thin, dry air of Antarctica and Hawaii, these telescopes scan the CMB for faint, swirling patterns called B-modes, the telltale fingerprints of primordial gravitational waves. These ripples in space-time, if detected, would be the echoes of inflation's violent birth, a smoking gun for the theory. So far, the search has been fraught with false alarms, like the controversial BICEP 2 announcement in 2014, where dust in our own galaxy mimicked the signal. But with each iteration, the instruments grow more sensitive, inching closer to either confirming inflation or forcing us back to the drawing board. Inflation's legacy isn't just about the past, it reshapes our view of the cosmos today. Those quantum fluctuations it amplified didn't vanish. They became the seeds for all structure in the universe. Every galaxy, every star, every atom in your body traces back to microscopic ripples stretched across the sky by inflation's relentless pull. Yet for all its explanatory power, the theory leaves glaring questions. What ended inflation? Why did space-time suddenly switch gears to the slower expansion we see now? Some models suggest it never truly stopped, that our universe is just one bubble in an eternally inflating multiverse, where new regions are constantly budding off into their own realities. This isn't just theoretical gymnastics. Inflation's mechanics might hold the key to the universe's ultimate fate. If the same repulsive gravity that drove inflation still lingers as dark energy, it could be quietly setting the stage for a far more dramatic finale, the big rip where the fabric of reality itself is torn apart. But that's a story for another moment. For now, inflation stands as a testament to the universe's ability to defy intuition, transforming the infinitesimally small into the astronomically vast in less time than it takes to blink. And as we peel back its layers, we're left with a humbling thought. The more we learn about the cosmos' birth, the more we realize how much of its story is still written in shadows. The universe isn't just expanding, it's accelerating, racing outward faster with each passing moment. And at the heart of this cosmic sprint lies dark energy, the mysterious force driving the acceleration. But what if this force doesn't just keep pushing galaxies apart? What if it grows stronger over time, becoming so powerful that it doesn't just stretch space, it tears it apart? This is the nightmare scenario cosmologists call the Big Rip, a catastrophic endgame where dark energies grip titans until it overcomes every force holding the universe together. First, galaxies would be ripped from each other, flung into the void like leaves in a hurricane. Then, stars would be torn from their galaxies, planets from their orbits. Finally, in the last agonizing moments, even atoms themselves would be shredded, their nuclei unable to withstand the overwhelming pull of space itself unraveling. The timing of this apocalypse hinges on a single, elusive number: dark energy's equation of state, represented by the variable W. If W equals -1, dark energy behaves like Einstein's cosmological constant, steady and unchanging, leading to a slower, colder demise as the universe expands indefinitely. But if W is less than -1, dark energy evolves, growing stronger as space stretches, accelerating the universe toward its violent end. Current observations place W tantalizingly close to -1, but the margin of error leaves room for darker possibilities. Some models suggest the Big Rip could occur in as little as 22 billion years, a blink of an eye on cosmic scales. Others argue it might take trillions of years, long after stars have burned out and black holes evaporated. But here's the twist: the Big Rip isn't inevitable. Our understanding of dark energy is still in its infancy, and new physics could rewrite the rules entirely. Perhaps dark energy weakens over time or transitions into another form of energy altogether. Some theories even propose that the universe could undergo a big bounce, collapsing back in on itself before a rip can occur, birthing a new cosmos from the ashes of the old. The uncertainty underscores how much we still don't know about the forces shaping reality. Yet amid this existential uncertainty, another possibility emerges, one far stranger and more hopeful. If the universe can end, could it also be just one of countless others, each with its own laws, its own fate? This is the Multiverse Hypothesis, where our cosmos is merely one bubble in an infinite froth of universes, some expanding forever, others collapsing, and some perhaps even avoiding destruction altogether. The Big Rip might be the end of our story, but in a multiverse, it's just one chapter in an epic far grander than we can imagine. What if our universe isn't the only one? Imagine a cosmic foam bubbling with countless other realities, each with its own laws of physics, its own versions of stars and planets, even its own bizarre forms of life. This isn't science fiction. It's the Multiverse Hypothesis, a radical idea gaining traction among physicists. The theory emerges naturally from eternal inflation, the notion that the Big Bang wasn't a one-time event, but a single bubble in an endlessly expanding sea of space-time. Picture a pot of boiling water. Steam bubbles form, grow, and detach from the surface. In this analogy, each bubble is a universe forever budding off from an eternally inflating background. Some might have stronger gravity, others with light that moves slower, or even dimensions we can't begin to visualize. String theory, the leading candidate for unifying quantum mechanics and gravity, adds weight to this wild idea. Its equations suggest there could be 10 to the 500 possible configurations of spacetime, each representing a unique universe with its own physical constants. That's a number so vast it dwarfs the atoms in our observable universe. In some of these worlds, stars might never form. In others, matter could be so unstable that atoms disintegrate instantly. Our universe, with its delicate balance allowing for galaxies, life, and consciousness, might be a rare statistical fluke, a single winning lottery ticket in a cosmic sea of losing ones. But how could we ever prove something so extraordinary? Some scientists hunt for anomalies in the cosmic microwave background, strange patterns that might be bruises from collisions with other bubble universes. Others look for evidence in the distribution of galaxies, searching for odd voids or alignments that defy standard cosmology. Then there's the quantum realm. Certain interpretations suggest that every quantum measurement spawns branching realities, creating infinite parallel worlds where every possible outcome plays out. While untestable now, future advances in quantum computing or high-energy physics might offer clues. The multiverse doesn't just expand our cosmic address, it shatters the very definition of reality. If countless universes exist, does reality mean anything beyond what we happen to observe? And if the laws of physics are just local bylaws in an infinite cosmic metropolis, what does that say about our search for a single theory of everything? These questions blur the line between physics and philosophy, forcing us to confront how little we truly understand about existence itself. Yet for all its grandeur, the multiverse hypothesis remains controversial. Critics argue it's not science if it can't be falsified. A universe we can't observe or interact with might as well not exist. Others see it as a natural extension of cosmology's most successful theories, the only logical conclusion if inflation truly is eternal. The debate isn't just academic, it cuts to the heart of how we define scientific progress. Are we content with theories that explain but can't be tested, or must we demand evidence, no matter how extraordinary the claim? This cosmic rethink mirrors another profound mystery, the nature of time itself. Just as the multiverse challenges our notions of space and reality, time's arrow, the one-way flow from past to future, defies our understanding at the most fundamental level. Why does time move forward, and could it ever reverse? The answer might lie in the chaotic dance of particles, the gravitational whirlpools of black holes, or even the quantum entanglement of distant atoms. But that's a journey into a realm where cause and effect, memory and prediction might not be as fixed as they seem. Every moment we experience, every sunrise, every heartbeat, every irreversible cup shattering on the floor, obeys an invisible cosmic rule. Time flows forward, never backward. This one-way street isn't just a quirk of human perception. It's woven into the fabric of reality by a principle called entropy, the measure of disorder in the universe. Imagine a deck of cards neatly arranged by suit and number. That's low entropy. Shuffle it, and entropy increases. The universe works the same way, constantly moving from order to chaos, making events like unscrambling an egg or unburning a log statistically impossible. But here's the twist. While entropy explains why time has a direction, it doesn't explain why the early universe started in such an improbably ordered, low-entropy state to begin with. That mystery is so profound that physicist Sir Arthur Eddington called it time's arrow, the irreversible trajectory that gives our lives causality and memory. Could this arrow ever bend or reverse? The laws of physics, strangely enough, don't forbid it. At the quantum level, particles don't care about time's flow. Equations work just as well backward as forward. Some theories of quantum gravity, like loop quantum cosmology, even suggest that a collapsing universe might rebound in a big bounce. with time effectively running in reverse during the contraction phase. Black holes add another layer of strangeness. Near their event horizons, time slows to a crawl due to relativistic effects, and some models propose that inside a black hole, space and time swap roles, meaning falling inward could be like moving backward through time. Wormholes, if they exist, might thread the needle further, creating shortcuts where time loops back on itself. Scientists aren't just speculating, they're testing these ideas in labs. Quantum entanglement experiments, where particles instantaneously influence each other across vast distances, hint at phenomena that might operate outside ordinary time constraints. In 2020, researchers even simulated a theoretical time crystal, a structure whose atoms repeat in time like a snowflake's pattern repeats in space, suggesting time itself could have subtle symmetries we've yet to understand. These aren't just academic curiosities. Cracking time's code could revolutionize everything from quantum computing to time travel. Imagine a future where we manipulate entropy like a dial, or harness closed time-like curves to send messages to the past. Yet for all our progress, time's arrow remains stubbornly pointed forward. The universe's initial low-entropy state, the Big Bang's pristine order, still defies explanation. Some theorists propose it's a statistical fluke in an eternal multiverse, while others wonder if time's flow is an emergent property, like temperature arising from atomic motion. Whatever the answer, the puzzle of time forces us to confront a deeper truth. Our perception of cause and effect, of past and future, might be just one slice of a far stranger reality. This brings us to another cosmic oddity that seems to mock our notions of order, the so-called axis of evil, a bizarre alignment in the cosmic microwave background that points suspiciously toward our solar system's plane. If time's arrow challenges our understanding of causality, this anomaly threatens to upend our view of the universe's very structure. The cosmic microwave background should be the ultimate cosmic fingerprint, a random, isotropic whisper of the Big Bang's afterglow. But there's something unsettling buried in its patterns. When scientists mapped its temperature fluctuations, they stumbled upon a bizarre coincidence. Those subtle hot and cold spots aren't entirely random. Instead, they show a peculiar alignment with the plane of our solar system, as if the universe itself is tipping its hat to our insignificant corner of space. Astronomers half-jokingly dubbed this the axis of evil because it shouldn't exist, not if the universe is truly homogeneous and isotropic, as the cosmological principle assumes. So is this just a fluke? The odds of such an alignment occurring by chance are less than 1 in 1,000, making it about as likely as flipping a coin and getting heads 10 times in a row. Skeptics argue it might be an artifact of measurement errors or foreground contamination, perhaps dust in our own galaxy, subtly skewing the data. But after multiple satellites, from WMAP to Planck, kept confirming the anomaly, that explanation started feeling increasingly shaky. This has led to more radical proposals. Could the universe be rotating on a grand scale, imprinting a preferred direction onto the CMB? It's not as far-fetched as it sounds. Black holes spin, galaxies spin, why not the cosmos itself? If true, it would upend our assumption that the universe has no special orientation. Even stranger is the idea that the axis might be a relic of pre-Big Bang physics, a cosmic scar left by whatever process birthed our universe. Some theories, like conformal cyclic cosmology, suggest our universe is one in an endless chain, with each cycle leaving faint traces in the next. The axis could be one such echo, a shadow of a previous eon. Then there's the most mind-bending possibility, external influence. If our universe is part of a multiverse, could gravitational tides from neighboring universes have tugged on space-time, leaving this odd alignment as evidence. It's speculative, but the axis's persistence forces us to consider options that would have been unthinkable a generation ago. What makes this more than just a cosmic curiosity is how it connects to the universe's geometry. If the CMB's anomalies reflect a deeper asymmetry, it could mean the cosmos isn't just a uniform expanse but has hidden structure, perhaps even a shape we've yet to comprehend. The axis might be a clue, a breadcrumb leading us toward answers about whether the universe is flat, closed like a sphere, or something even stranger. And that realization shifts the conversation from mere alignment to a far grander question. What is the true form of the cosmos we call home? If you set out on a journey through the cosmos in a perfectly straight line, would you eventually loop back to where you started, like a cosmic Magellan circumnavigating the universe? The answer hinges on one of the most fundamental questions in cosmology. What is the true shape of the universe? For decades, the prevailing assumption was that space is flat, a vast, infinite sheet where parallel lines never meet, and the angles of a triangle always add up to 180 degrees. This geometry isn't just mathematical elegance. It emerges from the universe's total density, a delicate balance between matter, energy, and the expansion rate. Measurements of the cosmic microwave background by satellites like Planck initially seemed to confirm this flatness with astonishing precision, matching predictions to within a razor-thin margin of error. But here's the catch. That margin, however small, leaves the door cracked open for mind-bending alternatives. Imagine a universe with just a fraction more matter and energy than we've measured, enough to bend spacetime ever so slightly into a closed, donut-like shape. In this scenario, space would curve back on itself like the surface of an inflating balloon. A beam of light traveling far enough would eventually return to its origin, and a spacecraft moving in one direction could, given enough time, complete a full loop of the cosmos. This isn't just theoretical whimsy. Some analyses of Planck's data hint at slight anomalies, a faint preference for certain large-scale temperature patterns that could suggest a universe with positive curvature. If true, the cosmos wouldn't be infinite but finite, like a cosmic version of the classic video game Asteroids, where flying off one edge brings you back in from the other side. On the flip side, there's the open universe model, where spacetime curves outward in a hyperbolic saddle shape. Here, parallel lines diverge, triangles bulge with angles summing to less than 180 degrees, and space stretches into infinite, ever-expanding emptiness. This geometry would arise if the universe's density fell short of the critical threshold needed for flatness. While current data leans away from this possibility, the uncertainty in our measurements means we can't entirely rule it out. The stakes here are more than academic. The universe's shape isn't just about geometry, it's a crystal ball for its ultimate fate. A closed universe might eventually stop expanding and collapse in a big crunch, while an open one would keep stretching into cold, endless dilution. Flatness, the current frontrunner, suggests a middle path, expansion that slows but never reverses, with dark energy's repulsive force tipping the scales toward an increasingly barren cosmos. This interplay between shape and destiny is why cosmologists obsess over the tiniest deviations in the CMB's temperature maps. A slight curvature could mean our flatness is just a local illusion, like an ant on a beach ball mistaking its surface for a flat plane. Yet for all our precision, the universe guards its true form closely. The Planck satellite's data, while exquisitely detailed, still carries uncertainties at the largest scales, the very scales where curvature would leave its clearest fingerprints. Future observatories, like the upcoming Euclid mission, aim to measure the universe's geometry with even finer precision, mapping galaxy distributions and gravitational lensing to test whether those tantalizing hints of curvature are real or mere statistical noise. Until then, we're left with a profound, humbling thought. The cosmos might be playing a trick on us, hiding its shape in the fine print of ancient light. This puzzle of cosmic geometry leads us to an even more perplexing frontier, the edge of the observable universe. If space is finite, what lies beyond its boundaries? And if it's infinite, how do we make sense of a reality without edges? The answers, much like the universe's shape, remain tantalizingly out of reach. We peer out into the cosmos, collecting light from galaxies nearly 46 billion light-years away, the very edge of our observable universe. But here's the unsettling truth: that boundary isn't the end of reality. It's just the limit of how far light has had time to travel since the Big Bang. Beyond that horizon, the universe almost certainly continues, perhaps infinitely, stretching into realms we can't yet see or even comprehend. This isn't just a matter of distance, it's a fundamental question about the nature of existence itself. Is the cosmos an endless expanse, or does it eventually loop back on itself like the surface of a globe? Clues to this puzzle might lie in the universe's largest structures. Take Laniakea, our home supercluster, a sprawling web of 100,000 galaxies spanning 500 million light-years, all gravitationally bound together. Yet even this colossal structure could be just one thread in a tapestry far grander than we've mapped. Some theories suggest that on scales beyond our observational reach, these superclusters arrange into even larger patterns, hinting at a universe that's not just vast but potentially infinite. But how could we ever test such an idea? One approach involves studying the cosmic microwave background for subtle statistical anomalies, tiny deviations that might reveal whether space curves gently over unimaginable distances or stretches on forever. The implications are staggering. An infinite universe means every possible configuration of matter must repeat somewhere, implying the existence of distant doppelgangers, regions where history played out almost identically to our own, complete with duplicate Earths and even versions of ourselves. A closed, finite cosmos, on the other hand, would mean everything eventually connects, like a cosmic Möbius strip where traveling far enough in one direction brings you back to where you started. Neither scenario is easy to reconcile with our everyday intuition, forcing us to confront how poorly our minds grasp the true scale of reality. This boundary also challenges our understanding of time. The galaxies at the observable universe's edge appear to us as they were billions of years ago, their light only now reaching us after an epic journey across expanding space. But what do they look like today? We'll never know, because the expansion of the universe ensures their current light will never arrive. Those regions are forever receding beyond our cosmic horizon, like ships vanishing over the edge of a flat Earth. Except this horizon isn't an illusion. It's a fundamental limit imposed by the speed of light and the relentless stretching of space itself. Yet even as we grapple with these limits, a radical idea emerges. What if the universe's true nature isn't three-dimensional at all? The holographic principle suggests that all the information in our three-dimensional cosmos might actually be encoded on a two-dimensional surface at its boundary, like a cosmic DVD where the movie we experience is projected from data stored on the edge. If true, it would mean the universe's vastness is an illusion, a kind of celestial sleight of hand where depth emerges from flatness. This isn't just philosophical speculation. It's a framework that could reconcile quantum mechanics with gravity, solving one of physics' greatest puzzles. So while we may never see beyond the observable universe's edge, its mysteries push us to rethink reality in ways that blur the line between science and profound existential wonder. The answers, if they exist, might not lie in traveling farther, but in looking deeper, questioning whether the universe's true frontiers are out there at all, or hidden in the very fabric of the dimensions we take for granted. What if everything you see, touch, and experience, every star, every mountain, every breath, isn't truly three-dimensional, but an elaborate illusion? The holographic principle dares to propose exactly that. Our seemingly vast, three-dimensional universe might actually be encoded on a distant two-dimensional surface, like a cosmic movie projected from the edge of reality. This isn't science fiction, it's a serious theory born from the study of black holes. When scientists calculated how much information a black hole can contain, they made a startling discovery. All the data inside could be perfectly represented on its two-dimensional event horizon, the point of no return. It's as if the black hole's three-dimensional interior is somehow written on its two-dimensional boundary, like a hologram where a flat surface creates the illusion of depth. This revelation led physicists to a radical leap. Could the entire universe work the same way? Imagine the cosmos as a giant sphere, with every event, every particle, every law of physics encoded in intricate detail on its outer shell. We, living inside the sphere, perceive these patterns as the rich, three-dimensional reality we know. The mathematics behind this idea isn't just elegant. It could solve one of physics' greatest puzzles, uniting quantum mechanics, which governs the tiny, with general relativity, which rules the cosmic. Quantum mechanics thrives in lower dimensions, while gravity emerges naturally from this holographic framework. It's as if the universe has been hiding its operating manual in plain sight, written in a language we're only now learning to read. But how could we ever test such a mind-bending concept? Quantum entanglement might hold the key. When particles become entangled, their properties link instantaneously across vast distances, as if space doesn't exist between them. Some researchers believe this spooky connection mirrors how information on the universe's hypothetical two-dimensional boundary could project into our three-dimensional world. Experiments like the holometer at Fermilab have searched for faint pixelation in space-time, tiny holographic noise that would betray the universe's true, lower-resolution nature. So far, the results are inconclusive, but the hunt continues. The holographic principle doesn't just challenge our understanding of space, it blurs the line between physics and philosophy. If reality is a projection, what does that say about consciousness, free will, or the nature of existence itself? Are we merely shadows on a cosmic wall, or is the universe's boundary the ultimate canvas for something deeper? These questions echo another controversial idea that our reality might not just be encoded, but simulated, like an advanced civilization's computer program. But that's a frontier where science and speculation collide, and it's waiting just beyond the next horizon. What if everything around us, the stars, the oceans, even your own thoughts, weren't real, but lines of code in an unfathomably advanced simulation? This isn't the plot of a sci-fi movie. It's the simulation hypothesis, a serious philosophical argument that's gained traction among scientists and thinkers like Nick Bostrom. His reasoning starts with three unsettling possibilities. Either advanced civilizations never reach the technological capability to create realistic simulations, they choose not to run them, or we're almost certainly living in one right now. Given the explosive progress of our own computing power, from room-sized machines to pocket-sized supercomputers in under a century, the first option seems unlikely. The second assumes a universal lack of curiosity, which contradicts humanity's own drive to explore and experiment. That leaves the third. If even a fraction of civilizations develop simulation technology, the number of simulated realities would dwarf the one base universe, making it statistically probable we're in a simulation. But how could we ever test such an outlandish idea? Some point to the quirks of quantum mechanics as potential glitches in the program. Take wave function collapse, the bizarre moment a quantum particle chooses its state only when observed. Could this be the simulation's way of conserving processing power, rendering only what's being measured to save resources? Others cite mathematical constants, like the fine structure constant, which seems suspiciously fine-tuned to allow life. Are these parameters hard-coded by our universe's programmers? Even cosmic speed limits, like light's unbreakable barrier, might reflect system architecture, a built-in limit to prevent processing overload. Yet for all its intrigue, the simulation hypothesis remains untestable with current science. It's a modern-day brain-in-a-vat problem, where any evidence we uncover could itself be part of the simulation. That hasn't stopped creative attempts to probe the idea. Some propose looking for pixelation in spacetime at the Planck scale, like a cosmic version of spotting the pixels on a TV screen. Others suggest hunting for computational shortcuts, places where the simulation might cheat by approximating complex physics, similar to how video games render distant landscapes with lower detail. So far, no such smoking gun has been found. The hypothesis's real power isn't in proving we're simulated, but in how it reframes our existential questions. If consciousness can be replicated digitally, what does that say about the nature of self? If our universe is someone else's experiment, does that diminish the meaning we derive from life, or does it amplify the wonder that we, simulated or not, can ponder our own origins? These questions blur the line between metaphysics and physics, forcing us to confront how little we truly understand about the fabric of reality. This cosmic identity crisis dovetails eerily with another profound mystery, the Fermi Paradox. If the universe is so vast and ancient, why does it seem so empty? Where are all the other civilizations? The simulation hypothesis offers one chilling answer. Perhaps they were never coded into the program in the first place. Or worse, what if we're an abandoned simulation, left running in some forgotten server? Our cosmic loneliness just an unintended consequence of a creator's disinterest. The silence of the stars might not be a puzzle to solve, but a glitch to debug. The universe is staggeringly old, around 13.8 billion years, and unimaginably vast, with hundreds of billions of galaxies, each hosting billions of stars. Given those numbers, the cosmos should be teeming with life, civilizations, and perhaps even interstellar travelers. Yet when we listen, the silence is deafening. No signals, no spacecraft, no evidence that anyone else is out there. This glaring contradiction is the Fermi Paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" The question isn't just curious, it's existential. If life is common, why does the universe seem so empty? And if it's rare, what does that say about our own place in the cosmos? One chilling answer is the Great Filter, a hypothetical barrier that prevents life from advancing beyond a certain point. Maybe the filter is behind us, meaning the emergence of intelligent life is so improbable that we've already beaten cosmic odds. Or worse, it's ahead of us, lurking in our future. Nuclear war, climate collapse, runaway AI, any could be the bottleneck that snuffs out civilizations before they reach the stars. The filter could even be something we haven't imagined yet, a universal trap that catches every society on the brink of interstellar expansion. If true, the silence isn't just puzzling, it's a warning. But there are less grim possibilities. Advanced civilizations might avoid broadcasting their presence, staying silent to evade predators or preserve resources. Imagine a galactic internet humming with encrypted signals we can't yet decode, or stealth probes hiding in plain sight, disguised as asteroids. Others could have transcended biology, uploading their minds into quantum supercomputers or Dyson swarms, leaving no trace we'd recognize. Some theories even suggest we're living in a cosmic zoo, intentionally isolated by a galactic community that's observing us like wildlife in a preserve. Then there's the sheer scale of space and time. The universe is so vast that signals or probes might not have reached us yet, or might have come and gone billions of years ago. Civilizations could rise and fall in the blink of a cosmic eye, their artifacts eroded by time. We've only been listening for radio waves for a century. That's less than a heartbeat in galactic terms. It's like standing in a desert for 5 seconds and concluding no one else exists because you didn't hear a shout. The paradox forces us to confront uncomfortable truths. Maybe we're the first, emerging in a young universe where life is just getting started. Or we're the last, the survivors of some ancient cataclysm that wiped out others. The answer might lie in uncharted regions, dark matter civilizations, hidden dimensions, or even our own future. One day, we might become the aliens others are searching for, spreading across the galaxy, and leaving others to wonder why the universe seems so empty. This brings us to humanity's next chapter. Will we remain passive observers or step into our role as cosmic explorers? The tools are advancing, from telescopes like JWST to ambitious projects like Breakthrough Starshot, but the choice is ours. The Fermi Paradox isn't just about them, it's about us. Are we destined to vanish into silence, or will we become the answer to someone else's question? The universe is waiting. Humanity stands at a crossroads between the familiar glow of our pale blue dot and the infinite dark beyond. For centuries, we've been cosmic spectators, piecing together the universe's secrets through telescopes and equations. But now, the line between observer and explorer is beginning to blur. The James Webb Space Telescope peers deeper into cosmic dawn than ever before, capturing light from galaxies born just after the Big Bang. Meanwhile, projects like Breakthrough Starshot aim to propel tiny probes to Alpha Centauri at a fifth the speed of light, turning science fiction into tangible mission plans. These aren't just incremental advances, they're the first tremors of a seismic shift in how we interact with the cosmos. Yet the leap from watching to voyaging is fraught with paradoxes. The same technology that could carry us to the stars also risks irrevocably contaminating pristine worlds with earthly microbes. Europa's subsurface ocean or Mars' ancient riverbeds might hold clues to life's origins, but one careless landing could erase that evidence forever. Then there's the ethical weight of expansion. If we find life, even microbial, do we have the right to alter its environment? These dilemmas force us to confront whether exploration, for all its nobility, might carry an invisible cost: the unintended arrogance of assuming the universe is ours to claim. The technological barriers are equally daunting. Interstellar travel demands energies rivaling supernova. Just to send a grapefruit-sized probe to a neighboring star within a human lifetime would require lasers with the combined power output of all civilization for months. And that's before grappling with cosmic radiation, micrometeoroid impacts, or the soul-crushing isolation of crews traveling for generations between stars. Some argue these challenges make robotic probes the only pragmatic path forward, preserving human curiosity without human fragility. Others counter that no machine can replace the irreplaceable, the wonder in an astronaut's eyes as they step onto an alien world, the cultural renaissance that would follow our first encounter with another intelligence. Perhaps the answer lies in redefining what it means to explore. Ancient Polynesians navigated the Pacific by reading stars and waves. Tomorrow's pioneers might ride magnetic sails through the solar wind or harness black holes as gravitational slingshots. The universe has always rewarded those who adapt to its rules rather than fight them. And if history is any guide, the urge to cross the next horizon isn't just a human trait, it's woven into the fabric of life itself. From the first microbes venturing onto land to the Wright brothers defying gravity, evolution favors the bold. This moment mirrors the universe's own story, an unfolding epic of expansion, complexity, and awakening. Every star we study, every planet we land on, is another verse in that grand narrative. Whether we remain watchers or become wanderers may depend less on physics than on something far more fragile and precious, our collective courage to embrace the unknown. The cosmos has spent 13 billion years preparing a stage vast beyond comprehension. Now it waits not with answers, but with possibilities as infinite as the stars themselves. The uncharted regions of the cosmos don't just defy our understanding, they redefine it. Every time we think we've grasped the universe's rules, it reveals another layer of mystery, another question lurking in the dark. Consider how far we've come. Just a century ago, we believed the Milky Way was the entire universe. Now, we know it's one of trillions of galaxies, each brimming with billions of stars, and yet, that staggering scale is still less than 5% of what's actually out there. The rest, a shadowy realm of dark matter, dark energy, and phenomena so strange they sound like fiction. But here's the beautiful paradox: the more we uncover, the more we realize how much we don't know. Take dark matter. We've mapped its gravitational fingerprints across galaxies, built detectors deep underground to catch its faintest whisper, and yet, its true nature remains just out of reach. Or dark energy, the force accelerating the universe's expansion. We've measured its effects with exquisite precision, but we still can't say whether it's a constant feature of space-time or a dynamic field evolving over time. Even time itself, the most familiar fabric of our daily lives, becomes a riddle when we peer into black holes or ponder the Big Bang's first moments. These aren't just gaps in knowledge, they're invitations to rethink reality from the ground up. And that's the thrill of exploration, whether it's across oceans or across the cosmos. The unknown isn't a void to fear, it's a catalyst. Every mystery solved, from the quantum foam's subatomic chaos to the cosmic web's vast filaments, doesn't mark an ending but a beginning. When the Event Horizon Telescope captured that first black hole image, it didn't just confirm Einstein's predictions, it opened new debates about what happens inside the event horizon. When JWST spotted galaxies older than theorists thought possible, it didn't close the book on cosmic dawn. It tore out the old pages and handed us a blank slate. Science at its best is a dance with the unknown, where every answer leads to a deeper question. So what's next? Maybe we'll find dark matter particles hiding in the data from a lab buried under a mountain. Maybe a repeating fast radio burst will finally unveil its origin, or a glitch in the cosmic microwave background will hint at a parallel universe, or perhaps the next breakthrough will come from something we haven't even thought to look for yet. That's the thing about the cosmos, it's always one step ahead, always ready to surprise us. Which of these mysteries captivates you the most? Is it the phantom tug of dark matter, the eerie silence of the Fermi Paradox, or the mind-bending possibility of a holographic universe? Drop your thoughts in the comments. I'd love to hear which cosmic puzzle keeps you up at night. And if you're hungry for more deep dives into the universe's greatest enigmas, hit that subscribe button. The journey doesn't end here. From rogue planets to quantum spacetime, there's always another frontier waiting. So keep looking up, keep questioning, and remember, the universe isn't just stranger than we imagine, it's stranger than we can imagine. Let's uncover its secrets